Welcome to the grand finale of our Wave Essential series. In this concluding part, we develop a deep into the intricate world of vibrating strings and harmonic, a symphony of physics and mathematics. Just like the soulful tones of saxophone, we will explore the harmonics that creates the magic in waves. Join me as we unravel the secrets, solve numerical puzzles, and ride the final wave towards a comprehensive understanding. Let's make our last dive into the waves of knowledge and emerge victorious. Are you ready? When a wire like EB is stretched between 2 points, a transverse wave travels along the wire and reflects at the fixed end. The reflection creates a transverse stationary wave as depicted in the figure. When a wire vibrates in one segment, wavelength λ1 is twice the length of wire, that is 2L. Therefore, N1, that is frequency first, is equal to V upon λ1. We know that velocity of a wave in a string or a wire is equal to V is equal to under root of T upon mu, fundamental frequency or first harmonics. Now consider a wire AB with length L and making it vibrate in one segment. The wavelength λ1 of the resulting stationary wave is equal to twice the length of wire, that is 2L. Therefore, L is equal to λ1 upon 2 or λ1 is equal to 2 times of L. This special condition, where the length of the wire is exactly half the wavelength, give rise to a lowest frequency known as fundamental frequency. The formula for the fundamental frequency N1 is given by N1 is equal to V upon λ1. We also know that velocity of a wave V on a stretched string is given by square root of tension divided by linear mass density mu of the string. Therefore, V is equal to under root of T upon mu. Substituting this expression for velocity into the fundamental frequency formula, we get N1 is equal to 1 upon 2L into under root of T upon mu. This equation describes the fundamental frequency of vibration for a stretched string, where L is the length of the string, T is the tension, and mu is the linear mass density. The fundamental frequency represents the lowest resonant frequency of the string. Second, harmonics. If the wire AB is made to vibrate in 2 segments when length is equal to λ2, the formula of the second harmonics is given by N2 is equal to 2 upon 2L into under root of T upon mu. Third harmonics. If the wire AB is made to vibrate in 3 segments, then L is equal to 3 by 2 into λ3 or λ3 is equal to 2 by 3 into L. The formula for the third harmonics N3 is given by N3 is equal to 3 upon 2L into root of T upon mu. General harmonics formula. For the mth harmonics, the equation is Nm is equal to m upon 2L into root T by mu, or Nm equal to m into N1. A string need not vibrate in one of those modes only. Generally, the vibration of a string will be a superposition of different modes. Some modes may be more strongly excited and some less. The musical instruments like sitar or violin are based on this principle, where the string is plucked or bowed determines which modes are more prominent than others. Laws of transverse vibrations. The following laws help us to solve the multiple choice questions quickly. Laws of transverse vibration of stretched strings are as follows. Law of length. For a given wire, mu is constant and T is also constant. The fundamental frequency of vibration is inversely proportional to the vibrating length. That is, N is directly proportional to 1 upon L, or NL is equal to constant. Law of tension. For constant length L and mu, the fundamental frequency is directly proportional to the square root of tension, that is N, is directly proportional to root of T. Law of mass. For constant L and T, the fundamental frequency varies inversely as the square root of the mass per unit length of wire, that is N, is directly proportional to 1 upon under root mu. This law provides valuable insight into the behavior of vibrating strings and facilitate a quicker understanding of related concepts. Physics of wind instruments. Musical wind instruments such as flute and saxophone create sound through a vibrations of air column within pipe. This phenomena relies on the superposition of incident and reflected waves, resulting in the formation of longitudinal stationary waves within the pipe. One prominent example of instruments utilizing air column vibrations is the organ pipe, a crucial element in producing the melodious tunes. Organ pipe exist in two main types: closed organ pipes sealed at one end and open organ pipes with opening at both ends. Longitudinal waves, often associated with sound waves, involves practical compression and rarefaction. In the context of air, compression corresponds to the regions of high air pressure, forming nodes, while the rarefaction corresponds to low air pressure regions, creating antinodes. Organ pipes in wind instrument. Closed organ pipe. In a closed organ pipe, when air is blown lightly at the open end, the air column vibrates in its fundamental node. This mode features a node at the closed end and an antinode at open end. Open organ pipe. Contrastingly, in an open organ pipe, when openings at both the ends, the vibrational dynamics creates a distinct pattern. When air is blown into the open organ pipe, the air column vibrates in the fundamental node, forming antinodes at the end and nodes in the middle. Closed organ pipe operation. Fundamental frequency and overtones. In a closed organ pipe, when air is blown lightly at the open end, the air column vibrates in its fundamental mode. The mode features a node at the closed end and an antinode at the open end. The fundamental frequency and one of these vibrations is determined by the length of the tube L. L is equal to lambda 1 upon 4. Note, 1/2 segment represent lambda by 4. Therefore, lambda 1 is equal to 4L. Now, from the formula for the velocity, V is equal to N1 into lambda 1. Therefore, N1 is equal to V upon lambda 1. Now, substituting the value of lambda 1 is equal to 4L, we get N1 is equal to V upon 4L. Third harmonics, N3. If air blown more forcefully, overtones and the frequencies higher than the fundamental frequency can be generated. Figure illustrates modes of vibration with two or more nodes and antinodes. For closed tube, we can have only odd-numbered harmonics. That is because closed tube, by the definition, have a node at one end and antinode at other. So, there is no way for even-numbered frequencies to be present. From figure, L is equal to 3 into lambda 3 by 4. Note, half segment represent lambda by 4 and the diagram shows 3 half segments. Therefore, lambda 3 is equal to 4L upon 3. Now, V is equal, that is the velocity of a wave, is equal to frequency into wavelength. Therefore, V is equal to N3 into lambda 3. Therefore, N3 is equal to V upon lambda 3. By substituting the value of lambda 3, we get N3 is equal to 3V upon 4L. As N1 is equal to V upon 4L, we get N3 is equal to 3 times of N1. Fifth harmonics. Figures show the formation of the fifth harmonics, where 3 nodes and antinodes at open end. The wavelength for the fifth harmonics, lambda 5, is 4 times of L by 5. L is equal to 5 lambda 5 divided by 4. Note, here are 5 half segment and half segment relate to lambda by 4. Therefore, lambda 5 is equal to 4L upon 5. Velocity is equal to n5 into lambda 5. Therefore, n5 is equal to v upon lambda 5. Substituting the value of lambda 5, we get n5 is equal to 5 times of v upon 4L. As n1 is equal to v upon 4L, we get n5 is equal to 5 times of n1. In closed pipe, only odd harmonics are possible. N1, 3 times of n1, 5 times of n1, 7 times of n1, 9 times of n1, and so on, can be represented by the general equation for mth overtone, and m is equal to into bracket 2m plus 1 bracket close into n1. First overtone is 3 n1. Second overtone is 5 n1. Third overtone is 7 times of n1. For mth overtone, number of nodes is equal to antinodes is equal to m. Fundamental frequency in open pipes. Moving on to the open organ pipe, characterized by opening at both ends. The air column vibrates in its fundamental mode. Antinodes are formed at the end of pipe, while node is established in the middle. If L is the length of the pipe, then the wavelength of the fundamental mode lambda 1. If we look at the figure, we have 2 half segments and 1 half segment is equal to lambda by 4. Therefore, L is equal to 2 times of lambda 1 by 4 or lambda 1 by 2. We can write it as lambda 1 is equal to 2 times of L. Velocity of a wave is given by v is equal to n1 into lambda 1 or n1 is equal to v upon lambda 1. Replacing the value of lambda 1 as 2L, we get n1 is equal to v upon 2L. This n1 is called as a fundamental frequency. Second, harmonics. As the vibration progresses to the next mode, additional nodes and antinodes are formed, as illustrated in figure. Note, 1 half segment represent lambda by 4 and diagram shows 4 half segments. In this case, the wavelength of a second harmonics, lambda 2, is equal to length of the pipe, or lambda 2 is equal to L. Number of half segments are 4 and half segment is equal to lambda by 4. Therefore, L is equal to 4 times of lambda 2 by 4 or L is equal to lambda 2. We know that velocity v is equal to n2 into lambda 2 and n2 is equal to v upon lambda 2. On replacing the value of lambda 2 as L, we get n2 is equal to v upon L. As n1 is equal to v upon 2L, we get n2 is equal to 2 times of n1. Third, harmonics. As shown in diagram, we have 6 half segment and each half segment is equal to lambda by 4. Therefore, tube length L is equal to 6 times of lambda 3 by 4 or L is equal to 3 by 2 of lambda 3. Velocity v is equal to n3 into lambda 3 or n3 is equal to v upon lambda 3. Replacing the value of lambda 3, we get n3 is equal to 3 times of V divided by 2L, as N1 is equal to V upon 2L. Therefore, N3 is equal to 3 times of N1. The frequencies of harmonics in open pipe. All harmonics are possible, that is 2N1, 3N1, 4N1, etc. The formula for the overtone frequency of nth overtone is Nm is equal to into bracket m plus 1 bracket close into N1, where m is the overtone. For mth overtone, the number of nodes is m and antinodes are m plus 1. As we have established the theoretical foundations of standing wave in string, open and closed pipes, let's now dive into some numerical examples to solidify our understanding. We will apply the formulas and concepts we have discussed to solve real-world problems and gain practical insight into the fascinating world of acoustics. So, buckle up as we shift gears from theory to numerical challenges, and let's explore the mathematical harmony behind the physics of musical wind instruments. The question from NEET 2023 question paper asked to find out the ratio of frequencies of fundamental harmonic produced by an open pipe to that of closed pipe having the same length. Now, the fundamental frequency of open pipe is given by V upon 2L, while fundamental frequency of closed pipe is given as V upon 4L. Therefore, if we take the ratio turns out to be 2:1. Option A is correct. In this question, asked to find the length of open organ pipe given, fundamental frequency in an open organ pipe is equal to the third harmonics of a closed pipe if the length of closed pipe is 20. Now, fundamental frequency of an open organ pipe is given as N1 is equal to V upon 2L. Here, L is the length of open organ pipe. Third harmonic of a closed organ pipe is given by N dash is equal to 3V upon 4L dash. Here, L dash is the length of the closed organ pipe. It is given that N is equal to N dash. Therefore, V upon 2L is equal to 3V upon 4L dash. Simplifying it, we get L is equal to 2 by 3 of L dash. It is given L dash is equal to 20 centimeter. On substituting the value, we get L is equal to 40 by 3, which is greater than 30. Option C is correct. This question is from NEET 2017 question paper. Here, they have asked to calculate the fundamental frequency of the system. Question describes two nearest harmonics of a tube closed at one end and open at other end are 220 Hz and 260 Hz. From the general formula for the equation of harmonics or overtone, note there is a gap of 2 between consecutive harmonics for a closed pipe. Therefore, into bracket 2m minus 1 bracket close into N1 is equal to 220 Hz. Then next frequency will be into bracket 2m plus 1 bracket close into N1 equal to 260 Hz. Subtracting the values, we get into bracket 2m plus 1 bracket close into N1 minus into bracket 2m minus 1 bracket close into N1 is equal to 260 minus 220. 2N1 is equal to 40 Hz or N1 is equal to 20 Hz. Option B is correct. Question is from NEET 2016 question paper. Asked to find the length of open pipe. Given the second overtone of an open organ pipe has the same frequency as the first overtone of closed pipe of L meters long. Open organ pipe second overtone given by the formula m plus 1 into bracket n1. Putting the value of 2, we get 3v upon 2l dash. Formula for the closed pipe overtone is given by the formula into bracket 2m minus 1 bracket close into n1. Substituting the value of m is equal to 2, we get 3 and 1 equals to 3 times of v upon 4l. Therefore, 3v upon 2l dash is equal to 3v upon 4l. On simplifying the equation for L dash, we get L dash is equal to 2L. Option B is correct. In this question, asked to find length of an organ pipe open at both the ends, given fundamental frequency of closed organ pipe of length 20 is equal to second overtone of an organ pipe open at both the ends. Fundamental frequency of closed organ pipe is given by N1 is equal to V upon 4L, and the formula for the overtone of open pipe is given by into bracket M plus 1 bracket close into N1. Substituting the value of M is equal to 2, we get 3 times of N1 is equal to 3V upon 2L dash. Comparing V upon 4L is equal to 3V upon 2L dash, and solving it further, we get L dash is equal to 6L. Therefore, L dash is equal to 6 times of 20, which is equal to 120. Option C is correct. In this question, asked to find number of possible natural oscillations of air column in a pipe closed at one end of the length 85 cm, whose frequency lie below 1250 Hz are. Now, natural frequency of closed pipe is given by N1 is equal to V upon 4L. Substituting the value of V and L, N1 is equal to 340 divided by 4 into 0.85. On simplifying it, we get N1 is equal to 100 Hz. Now, for closed pipe, only odd frequencies are possible: N1, 3N1, 5N1, 7N1, and so on. Therefore, 100, 300, 500, 700, 900, and 1100 are possible frequencies. Hence, 6 possible natural frequencies. Option B is correct. In this question, a cylindrical resonance tube open at both the ends has a fundamental frequency N in air if half of the length is dipped vertically in water. Asked to calculate fundamental frequency of the air column. The fundamental frequency for a pipe open at both the ends is given by N is equal to V upon 2L. Now, both end open pipe is dipped in water, therefore one end is closed. Fundamental frequency of closed end pipe is given by N dash is equal to 2V upon 4L. Therefore, N dash is equal to N1. Option C is correct. In this question, a closed organ pipe is excited to support the third overtone. It is asked to find out how many nodes and antinodes are formed in the air of the pipe. The third overtone for a closed pipe is fifth harmonics, thus 3 nodes and 3 antinodes. Option B is correct. In this question, a stretched string resonates with tuning fork of frequency 512 Hz when length of the string is 0.5. Asked to calculate the length of the string required to vibrate resonantly with a tuning fork of frequency 256 Hz. Now, we know that NL is equal to constant when T and mu is constant. Therefore, N is directly proportional to 1 upon L. Therefore, N1 upon N2 is equal to L2 upon L1. Simplifying it further, we get L2 is equal to N1 upon N2 into L1. Substituting the values of N1 as 512, L1 is equal to 0.5 and N2 is equal to 256. And simplifying it further, we get L2 is equal to 1 Option C is correct. In this question, it is given standing waves are produced in a 10-meter long stretch string. If the string vibrates in 5 segments and the wavelength is 20 meters per second, asked to calculate the frequency. Now, since it is vibrating in 5 segments, we can write as N5 is equal to 5 times of V upon 2L. V is 20 and L is 10. Therefore, N5 is equal to 5 into 20 divided by 2 into 10 equals to 5 Hz. Option B is correct. In this question, a sonometer wire, when vibrated in full length, has frequency N. Now, it is divided by the help of bridges into a number of segments of length L1, L2, L3 and so on. When vibrated, these segments have frequency N1, N2 and N3. Then we have to select a correct relation from given option. From the law of length, NL is equal to constant. Therefore, L is equal to K upon M. Now, L is equal to L1 plus L2 plus L3 plus so on. Therefore, K upon N is equal to K upon N1 plus K upon N2 plus K upon N3 plus so on. Therefore, 1 upon N is equal to 1 upon N1 plus 1 upon N2 plus 1 upon N3 so on. Option C is correct. As our wave journey gracefully concludes, we find ourselves riding the waves on musical tones where mathematics become our surfboard. Together, we have navigated through the intricate patterns of waves, seamlessly solving numerical challenges and dancing through the energetic crest. As I, Avinash, sign off for now, I want to express my heartfelt gratitude for your unwavering support and enthusiasm. Your engagement has turned this journey into the symphony of learning and exploration. Remember, learning is a continuous voyage and our paths will cross again. I humbly request you to like, share, comment and subscribe to our channel. Your support fuels our commitment to bring you more enriching content. Until our next exploration, may your learning be joyful and your exploration of the laws of nature be filled with wonders.